Good afternoon, everyone. Today we will be presenting on entangled state of quantum cryptography, specifically focusing on eavesdropping on the Eckert protocol. This is a part of our project course, Light Matter Interaction course. This is based on landmark papers by Naik in 2000 and Eckert in 1991. This is our team. We are the group of 6 members. So let's start with the motivation. Imagine Alice and Bob want to share a secret message over the internet. Today they use public key cryptography like RSA, which relies on mathematical difficulty of factoring very large number. For example, factoring 15 is easy. It's 3 and 5, but give a digit of 304, a digit number to a fastest supercomputer on the earth, but it would take longer than the age of universe to crack it. This sounds completely safe, but there is a fundamental problem lurking on the horizon. So the threat, in 1994, the Peter Shaw proved that the quantum cryptography can factor larger number efficiently in the polynomial times, not the exponential time. This changed everything once sufficiently powerful quantum computer exists. RSA encryption will be broken. All the encryption, internet traffic, banking, data, government communication become immediately vulnerable. This is known as quantum threat. The engine behind the Eckert protocol is quantum entanglement. When the two particles are entangled, they share a single quantum state measuring one instantly, and it determines the other no matter how the distance between them. It produces perfectly correlations in the same basis. The entanglement is used to generate identical random keys. More importantly, it ensures that any disturbance like eavesdropping breaks these correlations. So can a eavesdropper intercept in the quantum encryption communication, and can we catch up? We're implementing the Eckert E91 protocol using polarization, entangled photon pairs, and physically testing what happens when eavesdropper Eve tries to intercept the key. What we are looking for: does Eve interception disturb the entanglement between Alice and Bob? Does it introduce errors in secret key? Can we quantify exactly how detectable she is? The two detection methods are Bell inequality and bit error rate. So moving further, what is the experiment setup? The experiment setup consists, core components are laser source, which is an argon ion laser of 351.1 nanometer, provides a UV pump beam. It narrows line width, ensures the temporal coherence needed for quantum interference between the two vibrio crystals. Second, avalanches photodiodes, silicon single photon detectors with 60% efficiencies, narrow band filter placed for them, keeping photons from both crystals spectrally indistinguishable, preserving entanglement quality. Half wave plate, which is 22.5 degree, a fixed wave plate that combined with the liquid crystal gives access to specific elliptical polarization base required by the Eckert protocol. Calcite Klein-Thompson prism, a polarizing beam splitter separating the photon into two orthogonal outputs. One recorded as bit O and the other recorded as bit 1. Liquid crystal wave plate, a voltage control phase shifter in both Alice and Bob paths, changing the voltage randomly, switches their measurement basis for each photon in the real time. The last is BBO crystal SPDC source. The two adjacent BBO crystal, which is 0.6 mm each, with perpendicular optic axis. A 45-degree polarizing pump photon down converts in the either crystal, producing entangled pairs in the best state at 5,000 pairs per second. This is the experimental setup. This consists of 7 main components, and further my other teammates will continue.
Hello, myself Vedant Dubey, roll number 23B1836, and I will be explaining the Eckert protocol, which is the important part of the paper which talks about quantum cryptography, basically entangled quantum cryptography. So let me share my presentation. Okay, so this is what Eckert protocol is. So let's talk about the introduction. The Eckert protocol was proposed by Arthur Eckert in 1991, which is basically a quantum key distribution protocol. Means it is used to generate a quantum key in quantum communication using entangled photons. So, and another thing which will be used in this paper is Bell's inequality along with the Eckert protocol. So let's start. Why Eckert protocol? So in quantum cryptography, why Eckert protocol is used? Because its security is guaranteed by quantum physics. Means unlike the prime number factorization technique which is used to generate key, which is based on some mathematical computation, the Eckert protocol is basically based on fundamental physics and it is highly secure. Second thing is, any kind of spying on the information will completely disturb the system and we will be able to detect it. How? Everything we are going to see later. Then the protocol then helps us to generate a truly random key. That's why Eckert protocol is an important protocol in entangled quantum cryptography. So as we have discussed earlier also, the basic setup for this experiment is going to be like this. We will have a source which is generating entangled photon pairs. So basically it's going to be like this. We will have a source here which is generating entangled photon pairs, a source. Both photons are entangled. One photon will be seen to Alice. Alice and Bob are the two users who are trying to communicate, and Eve will be the spy. So Alice will be here, Bob will be here, and both entangled photon are getting shared to them. So, what are the experimental apparatus required? A source which generates entangled photons, two distance users, Alice and Bob, and both Alice and Bob should have measurement devices capable of measuring photons at different polarizations, which means they should be able to measure the photon and detect the photon in different bases. So what happens? The source produces entangled photons and then it sends one photon to Alice and one photon to Bob. Now let's see the very important part, step by step working of the Eckert protocol. So as we have discussed earlier, the step one is going to be the data collection. So basically what will happen, from the source, one photon will be sent to Alice and one photon will be sent to Bob. Both photons are entangled. Now what will happen? A random, like at a time, one photon will be sent. First photon, second photon, third photon. Okay, so photon will be sent. Now when the photon is sent, Alice and Bob will independently decide their own basis. Like Alice will decide its one basis, Bob will decide its one basis, and they will detect the photon. They will detect the entangled photon pair, and they will note down the basis which they use and the result they got using that basis. Then what will happen? They will get results kind of 0 or 1 and they are storing the basis plus result. This is data collection. They got all the data. Now after getting the data, what is important point here is Alice and Bob, regardless of spy is present or not, will share publicly which basis they used for every photon. Like if I send 5 photons, 10 photons, for every photon, Alice will say for the first photon, I use this basis. Bob will say for the first photon, I use this basis. Same for second photon, they will declare the basis. So for third, they will declare the basis. They are only sharing basis. They are not sharing the results which they got using that basis. So they will only share the basis. Now they will have all the data of the basis which they use. Now what they are going to do is, public sharing has happened. Now they will try to generate a key. So what is the idea to key generation? The data which they have received they will divide it into two parts. The first part is when those photons for which they use the same compatible basis, same or compatible basis. So Alice, like for first photon, Alice will say I used some basis, Bob will say I used same basis. So if they use same basis or compatible basis, then that photon will go to key. And for those results for which the bases were different, that photon will go to test data. So after all the data is collected, the data is divided into two parts. The first part is those photon pairs for which Alice and Bob use the same basis or compatible basis. That photon results will not be revealed and will be kept as secret for key. Second part will be those photon pairs for which the bases used were different, that will be used as test data, which we will use further to detect whether spy was present or not. Okay, so key generation is from same basis data. We will keep the result secret. We will not reveal it, and from that secret result, we will form a secret key. For different basis data, we will reveal the results, and then we used those revealed results to calculate correlations, which will tell us whether spy was present or not. Now the next last step is, how can we ensure whether the communication was secure or not? Basically, it talks about encryption. So as we have discussed earlier, Alice and Bob will receive photons regardless of regardless of spy was present or not, and they will divide the data into two parts. For the photons for which they use same basis, they will keep the data secret, and that will be key. And for the photons for which they used different basis, they will reveal the data, and that data will be used to calculate correlation factor, and that will be used to calculate Bayes parameter S. So Bayes inequality is something which talks on uh, how strong was the correlation and all that stuff. Shashank will be explaining Bayes inequality and more about rate of error and all that. Here I am mainly focusing on Eckert protocol. So after dividing the data and having the test data results, we will basically use those test data results to calculate correlation and Bayes parameter S. Bayes parameter S will tell us how strong was the correlation and how much error possibility is there. All these things. So using these correlations, we compute a value called S, which is Bell parameter, and this value tells us whether quantum entanglement is preserved or not. So as Shashank will explain, there is a value 2 at 2, which is the benchmark. So if the Bell parameter S is greater than 2, system is secure. Like no Ave or no spy was present. But if any spy was present, then what will happen? That system will get disturbed, results will get disturbed, which will lead to change in Bell parameter, and it will drop to less than 2. And when system is less than 2, we can say that spying has happened, or there was a present who was trying to decrypt the data. So basically, we have S as the Bell parameter. When it's greater than 2, communication is secure. When it's less than 2, communication is not secure. And how that 2 comes and what is Bell parameter, that will be explained more by Shashank. So these are the three core steps of Eckert's protocol. Now let's try to understand the same thing by an example, because example will give us more clear understanding. So let's suppose that we are sending 5 photons from source to Alice and Bob. Okay? 5 photons are getting sent. A1, A2, A3, B1, B2, B3 are Alice's basis and Bob's basis. Now here A2 is compatible with B2, A1 is compatible with B1, A3 is compatible with B3. So what's happening? I sent my first photon. Alice chose one basis, Bob chose one basis. Using that basis, Alice got some result, Bob got some result. Similarly, for other 4 photons, Alice will choose its basis, Bob will choose its basis, both will choose randomly, and they will note down their results. This is the first step. They are not sharing anything, they are just noting down the results. So these are the results. Now clearly we can see here the basis is compatible for first photon, for third photon, and for fifth photon. And for the second and fourth photon, the basis was different. Just note this thing. Now they collected the data. This is data collection. Second part is now public sharing. Step 2. What they will do here, they will just share only the basis used for every photon and not the results. They will not share what result they got. They will just share for first photon I use this basis, for second I use this basis, like that. Then two things: data separation and key generation. Data separation is for the photons for which they use same basis or compatible basis, A2 B2, A1 B1, A3 B3, like that. They will first identify those photons: photon 1, photon 3, photon 5. For this, they will not reveal the results. They will keep the results secret and form a key. That's what written here. key generation. Form key data from key data, results are kept secret, and we form a key. Like on the previous slide, photon one's result was 1 0 1, and when the bases used are same, both are going to get the same bits, like either 1 or either 0. If Alice got 1, Bob will also got 1. So key is formed. Now second part, test data, which is different bases. Here what's happening is, for the photons for which they use different bases, they will identify those photons, and for those photons they will reveal the exact results also. Like for photon 2, I got this, they will reveal the exact thing like this. For photon 2, Alice will reveal I got this, Bob will reveal I got this, 0 1 1 0, whatever it is. Now we will use this data to calculate correlation and Bell's inequality. And if the Bell's inequality parameter is greater than 2, our communication was secure. And if the Bell's inequality parameter is less than 2, then someone was there spying the data, which is a possibility. So that's the our whole Aves protocol. Now the next part, which is Bell's parameter, and more on how we got this number 2, will be explained by Shashank. Thank you.
And now what I'm going to be talking about is how do we detect eavesdropping using in Eckert's protocol using two things. One, Bell's inequality violation and bit error. So we're going to start. So what? Why quantum cryptography? We'll first start with that. Basically, in classical cryptography, we're using uh, factoring large primes as a way to encode and decode. But the current problem is that while technically, computationally, it's very intensive and very difficult, in recent times, due to quantum computers being built, and theoretically, in using Shor's algorithm, we can actually break this sort of classical cryptography. As a result, why we need to change the way we try to encrypt, and another way that we learned is basically using quantum cryptography. And how that works is basically we're using physics instead of just using simple maths, using proper physics and violation of such physics to be able to be tell if anyone is eavesdropping between channel A. So what is Eckert's protocol? I'm just going to give a brief overview. Basically, Eckert's protocol source gives out two an entangled pair of photons, one to Alice and one to Bob. So basically, they are in an entangled state, and they each Alice and Bob chooses four bases, and they test certain combinations, and only in certain combinations they actually build the cryptography. The other bases are other combination bases are used to test Bell's inequalities, and I'll show you how. And this actually helps us to be able to prove if there was an eavesdropper interfering between that in that channel. So basically, I'm going to give a brief overview of what entanglement is. So let's say since Alice and Bob receive one photon from the entangled pair, these are created together in a state where the polarizations are completely correlated. So they are not programmed anything like that. Physically, they are correlated. They have a quantum correlation to each other. So there's no classical explanation. And if Alice measures a photon, obviously Bob photon knows immediately, and immediately will be its result will be instantly determined. So these correlations are anything much stronger than what classical physics will do. So it is also irrespective of distance also. And actually one of the best things to this is that entanglement is very fragile. So if one of the photons were measured, it will disrupt the other photon as well. So, and the final nail in the coffin would be that the no cloning theorem says that it cannot be copied. So, if anyone were to try to replicate such an entangled pair of photons, it's not possible physically, not possible at all. So, how do we prove it? We have to prove it in such a way that we'll be able to tell that this entanglement has been broken. And one such way is Bell's inequality. So what is Bell's inequality? Is basically it's like a test to see if the correlation is classical or quantum. So there's a Bell parameter to this, and they try to calculate this. I'll show you in the next slide, where we try to compute Bell's parameter, and in a classical theory, it should be less than 2. But in a quantum entanglement is a quantum phenomenon, it basically disrupts this uh, inequality, and thus it's in quantum mechanics it's uh, actually 2 root 2, which is much greater than 2. But in our scenario, in our experiments, what we have seen is that it is slightly lesser than 2 root 2, but much greater than 2. So most definitely we'll be able to show that in an experimental or a real world basis that as long as the Bell's parameter is greater than 2, we should be able to disrupt Bell's inequality. And also, if there were someone trying to interfere between the two channels and disrupt this entanglement, we'll be immediately able to tell through Bell's parameter that it would have gone down to less than 2. So how is it calculated? Basically, it has been defined using correlation functions in certain measurement bases A and B, and using that we look at the addition of all these correlation functions. So the correlation function basically is defined by how many photons and how many results where both of them agree +1, and if both results are the opposite -1. So as long as they agree with each other, they are added, and if there is a disagreement with each other, then they are removed. So we're looking at this number, we'll be able to tell with addition of all this, we'll be able to calculate the Bell's parameter and be able to tell using if there is a high entanglement or high is it a quantum entanglement or it's just a classical correlation. So how do Eve destroys this entanglement? Obviously, if there is an entangled photon pair, Eve intercepting and measuring it disrupts the pair entirely. And what Eve has to do once it intercepts that photon, it tries to send that same photon back. But the thing is, the entanglement has already been destroyed. What Eve is trying to do is basically just sending a random photon, and since it's just a classical correlation, the only issue that you will have is that its correlation function, I mean, its Bell's parameter would be less than 2. It's just how the physics shows, and also that entangled photon cannot be cloned, as the nuclear theorem shows that it cannot be an entangled quantum photon cannot be replicated or cloned, basically. So yeah, as I said, uh, yeah. Now we're going to talk about bit error rate. So bit error rate is much simpler, where Alice and Bob use certain measurement basis combination. With the quantum mechanics says that it should be completely perfectly correlated, and let's say if Alice measures 0, Bob must also measure 0. So the matching results will form that cryptography key basically. what bit error rate is, it's just what fraction of the keys bits disagree with each other. Technically, if there was no eavesdrop or anything like that, in an ideal case, it could be zero. But why would Eve even introduce error in it? Technically, what you're sending is basically the same bit that technically she received. She, but the thing is, Eve does not know what measurement basis Alice and Bob are using. She, they are completely random, and they will only discuss after the measurement. So when Eve measures a photon, she measures in a basis that is not that may or may not be equivalent to the basis that Bob chooses. So she guesses wrong, then it disrupts the photon state, and when Bob measures that same photon, there's going to be a probability that it disagrees with Alice's again. So now then we'll get an error now, like where there shouldn't be. So that minimum in which you would get that error in a perfect like the bare minimum that it should be would be 25%, because even if Eve was as perfect as possible, there is a bare minimum because the error rate when trying to intercept himself has a 50% chance, and again when she tries to send it back another 1 by 2 chance. So multiplicative to each other, it will be a bare minimum of 1 by 4 chance of having that quantum state be disagreeing with each other. So as I can show you later. So these are the two independent. Basically, they are independent to each other, but there is some correlation to each other, where the Bell's inequality tests the physics of the channel itself, and show that the entanglement is intact. So while the bit error rate uses statistics to be able to show if there is any issue, if there is any interference between the two channels. So in a perfect world, obviously you wouldn't try to intercept all the photons that Alice sends to Bob. What if we were to do in such a way where Alice actually, so now we'll try to look for a correlation where we'll try to look for a middle ground where he tries to intercept a few photons, not too many, so that she gets detected, but enough where she gets enough information. And according to the paper, for to get be able to measure Bob's basis, to be able to predict Bob's basis, he needs at least 58.6 percentage of the photons intercepted. So that is way too much, because even trying to get a few photons will try to increase the bit error rate, and as a result, obviously the well parameter will collapse, and thus Alice and Bob will be able to tell immediately. So having that middle ground is fairly difficult and impossible. So obviously the experimental results show that the measurement bit error rate was just 3.06%, well below the 25% threshold. And it's even low error rate can be attributed to certain optics and how the detectors work. So even after error correction and privacy amplification, we get 15,444 truly finalized secret bits, which were generated from raw data and without any potential eavesdropping. So what this tells us is basically that no matter how Eve tries to interfere with the results or tries to gather information, there's a there will be no way without being detected immediately, and thus in my conclusion what I'm going to say is that it's using Eckert protocol is using entanglement as a physical guarantee and not like a computational guarantee where classical classical
to detect any eavesdropper. Security is guaranteed by the law of quantum physics. So Alice and Bob each receive one photon from the entangled pair in the state 5. They measure it randomly in the elliptical polarized bases, liquid crystals and prism. Certain basis combination yielding the secure key, and others are used in testing the Bell's inequality. If an Eve interprets the photon, she disturbs the entanglement, which is shown as a reduction in the Bell's parameter S, an increase in a bit error rate. So let's start with our notebook. These are the library we have loaded. After that, the paper uses the elliptical polarized spaces. M is equal to H plus E alpha V under root 2. And the correlation function for the Bell state is EAB is equal to minus cos A plus B. So we tried simulating this correlation function with the help of the NumPy. So we started with the H and V states within NumPy array, and then defined the phi minus and rho, the density matrix. And then we got the Bell state is this as we defined earlier. The amplitude came out to be this in the norm and the density matrix. And other part, we use the correlation function quantum as we defined for calculating our correlation functions value. And the code is given as well. And it matches with the paper formulas. So what this correlation in this. So it's represented as a density matrix using the NumPy. So NumPy outer function we are using for the density matrix. So the density matrix is not just a convenience. It is the central mathematical object that is very substantial calculation in the notebook operations or on. So it encodes the perfect intercorrelation between Alice and Bob photon. Meaning whenever Alice measures a spin up along some direction, Bob is guaranteed to measure spin down along the same direction, and vice versa. This perfect anti-correlation maintained across distance is the physical foundation that makes the protocol work both for key generation and sensitive to eavesdropping. So further, the confidence probabilities. So as defined in the paper, P12 AB is equal to 1 by 4, 1 plus cos A plus B, and P12 dash A plus AB is 1 by 4, 1 minus cos A plus B. So when A plus B is 180, P12 is 0, and P half is 0.5, and perfect anti-correlation relation. So given a single state, we calculate the probability that Alice measures along A and the Bob measures along B. 4 combinations output are there: up, 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 down, up, and down, down. So the key used here is the correlation. So we have plotted a graph for like we are taking the Alice angle as 45 and the Bob angle as from 0 to 360. So A plus B is equal to 180 this, and this is correlation, this is anti-correlation. So in this part, we try to create the table 1 of the paper. So Alice has A1, A2, A3, A4 from 45 till 180. And similarly, Bob has from 0, 45, 91, 35. So we can take the combinations and make it 180. So there are like 16 bits created, and the Q 25 there are Q keys which we can use in making the key. So their sum is 180. So we can use this as the secured key we will create. S and S dash are for the Bales operations, and the remaining 25% are unused. So next we are calculating the Bales inequality. S and S dash calculation. So we have the formula for S as minus E A1 B1 plus E A1 B3 plus E A3 B1 plus E A3 B3. So the correlation we know already minus cos A plus B. So we are taking the same 4 angles for Alice and 4 angle for Bob, so that the sum is 180. And then we are calculating the S and S dash. And similarly, so this is the Bellman parameter versus angle offset. So how these are changing. So this S is the we are getting from the Bellman from here S theory, and for each angle for 0 to 90 degrees. So the theoretical S is supposed to be 2 root 2, and the theoretical S dash is that we are getting is 2 root 2, and the paper showed it to have to be this. So we know that the classical bound is that F should be less than 2, that is the red one, and the quantum max, the maximum value according to the quantum mechanics we can get is 2 root 2. So the maximum we are getting is also 2 root 2. If Eves interpret also, so if he get all the values, so that then the S value is root 2, and the paper shows this one, which is 2.62 and error. So the using the specific 4 angles design. So in uneavesdrop channels, the quantum predicts that that should be root 2. And similarly, we have drawn the bar graph for this. This is the classical one. This is when E interprets all the photons and the. So next is the key generation simulation. So for key bit pair A plus B is equal to 180, the entangled state gives a correlation output equal to 1. So it generates a long sequence of random measurement events, applies the applied joint probability derived from the density matrix, and filter on only those events where Alice and Bob's happen to use the same key generation basis. So we are only taking the basis where Alice and Bob have the same basis. We are taking the values where the Alice and Bob have the same basis. From these events, it extracts 1 bit per event and assembles 2 bit strings, one for Alice and one for Bob, which is printed side by side in the output. In a perfect noiseless simulation with no errors, these 2 strings are completely identical. So this shared the secret bit string in the row quantum key. So like these are the angle we chose, and we tried 1 lakh and pair. So the key bits were 2, 5, and 4 that were generated. As for 1 lakh, we expected 25% of that. And this is approximately same. So the simulated BER, we calculated that the BER for these keys, for the generated keys, and that came out to be like so. What the notebook computes the BER error between Alice and Bob row keys, and the ideal no eavesdropping case, the BER should exactly be 0. Every bit matches. So this section estimates a clean baseline, and the BER will become the center tool in the next section, because the moment Eve enters the picture and starts interpreting photons, this number rises in a measurable and predictable way that exposes her presence. So like there is no error in the earlier keys, and there's no error in the first key, because both Alice and Bob have the same key in the same basis. So if I run it again, so it depends upon the it's randomly, we are generating the bits randomly, so there are chances that some bits can have in the same, and there are different bases, and the key is same, so there can be some error. So from that we calculate the BER value. So we have simulated BR value. We calculated the BR value there, and then plotted the graph and our BR and the paper BR. So next part is reproduction eavesdropping effect on S and BER. So the most important section of the notebook, and it directly reproduces the plot figure 2 from the paper. So the notebook model Eves attacked using a crops operator applied to the density matrix. When an Eve interprets Alice photons and measure it before passing it to Bob, she disturbs the entangled state, and this notebook then recomputes both S and BER from the damaged state and plot how they vary as Eve rotates their measurement pieces. So we are taking 3 bases: elliptical, linear, and diagonal. So then we calculate the S and BR value for all the plots, and these are the functions for those. So this is saying if there is no Eve, and we then try to find the BR, we get 0. And if there is a presence of Eve, that then S is root 2, and BR we get is 25%. Next, these are the plot for the elliptical part. So in the first part, we are using the elliptical basis. So Eve measurement basis lie in the same elliptical plane as Alice and Bob. Because of her basis is geometrically aligned with the protocol plane, the overlap between her attack and the measurement basis is constant. No matter which angle C picks within that plane, the result is a plane horizontal line for both S and R across all Eve rotation angles. So BR still is at 25. So this is the best case for Eve. She causes the minimum possible disturbance while interpreting every photon. So the next part is linear. Eve uses a linear polarized state, which lives on the equator of a pentacured sphere, a completely different plane from Alice and Bob, as Alice and Bob are using elliptical basis. As Eve rotates her polarized plane from -90 to 90, her basis is sometimes well aligned with Alice's current measurement direction and sometimes nearly orthogonal to it. So this continuously changes the geometry overlap, produce sine oscillations in both S and BER curve across a rotation angle. So the average BER across the full rotation rises to 32. So this is the orthogonal plane BR 32.5, making it significantly more that she will be detected. And in the third part, she is using the diagonal basis. So Eve uses the diagonal basis. The average BR is again 32.5, but the phase of sinusoidal is shifting related to the second geometry because the diagonal shifts at the different orientation related to the Alice and Bob. So the phase difference is clearly visible in the both plots and the BR value. So for the panel A, when both Eve's basis was same as Alice and Bob, the S was √2 and BR was 25. So maximum could have 50 in the later two cases, and similarly S could have a maximum of √2. So the next part is partial eavesdropping. So there was a threshold given in paper for 58.6 threshold. The paper states that if Eve measures less than 58.6% of photon, then S is greater than 2 and BR is less than 15. So let's try. We are using a partial rho function. For this is the value for mod S is equal to 1 by F into when there is no Eve plus F into when there is Eve. So when there is no Eve, the S is 2 √2. When Eve interprets all, the S value is √2. So the partial will be 1 minus this F value, which we are the fraction of photon we are getting into 2 √2 plus the fraction of photon into √2. So really, so whenever Eve interprets only fraction of photon rather than all, as the interpretation fractions goes from 0 to 1, both S and B are grade smooth and continuous. There is no safe threshold below which Eve is invisible. Even interpreting a small percentage of photons leaves a statistical detection signature in the correlation data. So it makes sure that Eve is present. Yeah, so this is S versus Eve's fraction. So how much fraction it is present? If it's 0%, so the S is maximum. And Eve is fully present, that's 1.4. So the classical bound is 2. So when there is no Eve, then when there is no Eve, 0 Eve, that's 2.8. And so the threshold is when it is crossing the classical limit, it's at a 58.6. So Eve detectable part is this. If Eve is present in this much percentage, it's easily detectable and not detectable by S if it's in the red area. Similarly, for the BR value also, if it's below 50%, we can check it's 14.6. So is easily detectable.
So, I will be talking about privacy amplification pipeline. After the rock key has been generated and the eavesdropping check has been completed, the notebook applies a critically important final step called privacy amplification. To understand why this step is necessary, consider the following situation. Even after Alice and Bob have confirmed that S is close to 2.828 and that BER is within acceptable limits, there is still a possibility that Eve intercepted a small number of photons and gained partial knowledge of a few bits in the rock key. She does not know the whole key, but she knows something. Privacy amplification is the mathematical technique that takes that partial knowledge and renders it completely useless. The way it works in the notebook is through a hash function. Alice and Bob publicly agree on hash function after the quantum transmission is already complete. They then both apply this hash function to their raw keys, which compress the key down to a shorter length, which is shown on the screen. The crucial point is that because the hash function is chosen after the transmission, Eve had no way of knowing in advance which function would be selected. This means that even if she intercepted 10 bits out of 100, her knowledge of those 10 bits gives her essentially zero information about the final hashed output. The compression mathematically washes out her partial information. The notebook demonstrates this step by computing how much the key must be shortened based on estimated number of beats. Eve may have learned the more interception that is suspected. The shorter the final key becomes, the output is a reduced but probably and information theoretically secure final key, meaning this its security does not rely on computational hardness but on the laws of mathematics and quantum physics themselves. We can see the graph on the screen. First, these are initial bits, and 18,298 are the error correction bits after error correction, and after privacy amplification we get the 15,444 bits. Next, talking about 6-state protocol, the notebook concludes with a comprehensive summary table that serves as the final verification of entire implementation. This table places every key metric from the paper directly alongside the corresponding value computed by the notebook. It includes the bell parameter S for the no eavesdropper case, the BR values for all three eavesdropping geometries, uh, the aligned elliptical plane at the 25%, and the both linear and diagonal planes at 32.5%. The partial interception result showing smooth degradation across interception fractions, and the final key generation rate after privacy amplification. Every single number in the table matches the paper. This is most important result of the notebook because it means the implementation is not approximate or illustrative. It is an exact computational reproduction of the paper's experimental findings using nothing but pure Python and NumPy. To summarize what this notebook achieves as a whole, it starts with this notebook achieves a density matrix representing an entangled photon pair, builds the full measurement probability framework from quantum mechanics, generates a secret shared key, detects eavesdropping through Bell inequality violation, models three geometrically distinct attack strategies, handles partial interception, applies privacy amplification, and varies every result against the published paper. The entire Eckert protocol, one of the most elegant ideas in quantum cryptography, is contained and verified within this single notebook. State generation. So the photon pairs are generated in this experiment. I will tell about that. So method used is SPDC down conversion, which is standard technique in quantum optics to produce entangled photons. In this setup, the researcher used two identically cut BBO crystals, each of length 0.6 mm, placed with their optic axis perpendicular to each other. This configuration is very important for creating entanglement. A 45-degree polarized pump photon coming from a laser enters the crystal. Now here's the key idea. This photon has equal probability of converting in either of the two crystals. If it converts in the first crystal, it produces two photons with horizontal polarization. If it converts in the second crystal, it produces two photons with vertical polarization. Because these two processes are indistinguishable and coherent, the system does not choose one outcome, it exists in superposition of both. So the final state becomes maximally entangled state. Both photons are correlated in such a way that measuring one instantly determines the other. This is exactly the Bell state, which is essential for the Eckert quantum cryptography protocol used in the paper. So talking about Alice and Bob's analysis statement, each station, Alice and Bob, has identical setup consisting of three main components. First, liquid crystal. This is randomly driven and is used to apply phase shift effectively, allowing Alice and Bob to choose different measurement bases randomly. This randomness is crucial. And second one is half wave plate, which is optic axis set at 22.5 degrees.
This rotates the polarization of incoming photons so that different measurement bases can be accessed. Third is the polarizing beam splitter, specifically a calcite gland Thomson prism. This splits the incoming photon into two paths based on polarization, horizontal and vertical. So measurements can be made. Now coming towards detection, they use silicon avalanche photodiodes, which have about 60% efficiency and very low noise to ensure accurate detection. They also use narrow band filters to select specific wavelengths, a 5 nanosecond coincidence window, which ensures that only photon arriving together are counted as a pair. Because of this precise timing, the accidental coincidence rate is extremely low, about 10 raised to 5 per second. In fact, the system achieves a high coincidence rate of around 500 counts per second, which ensures a good data collection. So overall, random basis selection is done using liquid crystals, and optical elements control polarization measurement. हाँ, फर्स्ट पार्ट तो हो गया वैसे तो. So now I will explain how the system operates in terms of timing and how data is used for security. First, the collection window is 1 millisecond. This means the system only records one photon per time window to avoid multiple pair interference, which could leak information. Next, the liquid crystal cycle period is 22 milliseconds, which determines how fast the measurement settings can change. Because of this, the maximum data rate is about 45.4 hertz. But in practice, we get around 40 usable photon pairs per second. Now, an important part of the Eckert protocol is how the collected data is divided. So, 1/4 of the data used is used to generate the raw cryptographic key. Half of the data is used to tell Bell's inequalities, and 1/4 of the data is discarded. This is crucial because, unlike classical cryptography, security here is continuously verified using quantum correlations rather than assumed. So essentially, we sacrifice some data to guarantee security. Now talking about performance and privacy amplification. Now, in 4 experimental runs of 10 minutes each, the system generated about 24,252 raw key bits with a bit rate of around 10.1 bits per second. The bit error rate was about 3.06%, which is relatively low, but still important because errors can indicate either noise or eavesdropping. Now comes the critical part, estimating how much information an eavesdropper might have. Using a conservative estimate, Eve could know about 2,500 bits due to multiple photon emissions intercept recent attacks. To eliminate this risks, two steps are performed. First is error correction, which reduces the key to 18,298 error-free bits. Then privacy amplification, where the key is compressed further to 15,444 secure bits. This step ensures that even if Eve have partial information, it becomes negligible. Finally, the net secure bit rate is about 6.4 bits per second, and remaining information accessible to Eve is approximately 1 bit, which is practically zero. हो रहा. Now, I'll compare two types of photon sources used in quantum cryptography, single photon sources and SPDC sources. Starting with single photon sources, ideally these emit exactly one photon per transmission. This is perfect for security because it prevents photon splitting or duplication. So if an eavesdropper tries to intercept the photon, it will always introduce a disturbance that can be detected. However, in practice, two single photon sources are difficult to build. Most real systems use weak laser pulses, which can sometimes contain more than one photon. This creates a security loophole. For example, an eavesdropper can intercept one photon and let the others pass through undetected, gaining information without introducing noticeable errors. Um, Now coming to SPDT sources, which stands for spontaneous parametric down conversion. Here, one high energy photon is converted into two lower energy photons using nonlinear crystals. These photon pairs are naturally entangled, which make them very useful for protocols like the Eckert protocol. SPDC sources have several advantages. They are easier to implement experimentally. They produce strong quantum correlations, and they allow direct testing of Venn inequalities. For security, another key feature is they provide intrinsic randomness and allow real-time detection of eavesdropping through correlation measurements. So overall, while single photon sources are theoretically ideal, SPDC sources are more practical and are widely used as real experiments. Now talking about pair SPDC and double pair effects. Now I will explain how SPDC generates photon pairs and an important issue called the double pair effect. In SPDC, we use nonlinear BBO crystals. A pump photon enters the crystals and splits into entangled photons. This entanglement is the key resource used for generating cryptographic keys and testing Bell inequalities. However, there is an important limitation. Sometimes the SPDC process produces more than one pair. At the same time, this is called a double pair or multi-pair emission. Instead of two photons, we may get four or more photons. This creates a security issue. Extra photons can be intercepted by eavesdropper, and Eve can gain partial information about the key, and this reduces the overall security of the communication. In the experiment, this problem is handled carefully because there is a high probability of multiple pairs within a detection window. The system only considers the first detected photon pair and ignores the rest. This reduces the risk of copying, but does not eliminate it completely. There is still a small residual error, about 0.7%, which is taken into account during security analysis and removed later using privacy amplification.
Hello, my name is Saurabh. So far in this presentation, you must have worked across theory, setup, and data. My job is to bring it all together. What does this experiment actually prove? What are its limits, and where does any of this matter to? Let's start with the results. The team at Los Alamos successfully implemented the ERIC protocol end-to-end. Real photons, real detector, real measurements, not a simulation, not a mathematical model, and actual working quantum cryptographic system. The headline number is Bell's parameter. They measured it as a 2.665. The classical limit is 2. The quantum mechanical prediction is 2.83. The result cites 34 standard deviation above the classical limit. That's not a close call. That's an overwhelming confirmation that the system was genuinely quantum mechanical. And after all the error correction and the privacy amplifications, they did end up with 15,444 secure bits, and Eve's total knowledge across the entire key was approximately 1 bit. The physics delivers exactly what the theory promised. So now the part that makes this paper stand out, they didn't just build a protocol and hope no one was listening. They actually built an eavesdropper and tested her. Two strategies were investigated. The first is stronger projective measurement. Eve physically intercepts a polarizer into Bob's photon path, measures the photon, and resends the surviving photon to Bob. If she picks the right pieces, the same plane Alice and Bob are measuring it, she causes 25% bit error rate. If she picks the wrong basis and orthogonal plane, her error rate climbs to 32.5%. Either way, she loses the case. The second strategy is pseudo QND attack. A true quantum non-demolition measurement would let Eve extract information without disturbing the photon at all. That's not physically possible yet. But the mathematical effect of such measurements introducing a random phase between polarization components can be replaced with a thick bare fragment crystal, and her and here's the key finding. The result is systematically identical to strategy one, but both attacks completely different physical mechanisms, same detectable fingerprint in data. So what's actually new here? This slide I want you to remember before the paper eavesdroppers in quantum cryptography experiment were theoretical. Eve was introduced in post detection computations. They existed in math, not in the lab. The experiment was the first to place a physical eavesdropper directly in the optical path between Alice and Bob. The effect was exactly as predicted, with no eavesdropper The parameter is 2.665 with Eve intercepting every photon that drops to root 2, which is approximately 1.41. That's a dramatical fall from well above quantum limit all the way down to down below the classical limit of the practical implementation in the setup. Eve's presence would be statistically detectable with 1 second of data collection. 1 second, and no matter how clever her strategy, privacy amplification, or end reduces, whether she load to essentially 1 bit. Across the entire key, she can interrupt, she can measure, she can resend, and she still end up knowing almost nothing. Limitations. Every honest conclusion acknowledges what didn't work, and this paper does the same. The most obvious limitation: Alice and Bob were sitting next to each other at the same optical table. That's not cryptography, that's a lab demonstration. Real cryptography requires distance, and this experiment had essentially none. The bitrate was also extremely slow, 6.4 secure bits per second after all processing. The liquid crystal switching measurement we had a cycle of 22 milliseconds, which sharp data collection severely. Modern systems use electro-optic modulators and that switch in nanoseconds. The author themselves mentioned in the obvious upgrade path. And the double pair problem, occasionally the source emitted 2 photon pairs instead of one. They gave a hypothetical eavesdropper a small window, about 0.7% of the key bit potentially exposed. But here's the important framing. None of these are fundamentally physical problems. These are engineered problems. The author knew this, and they said so explicitly. The impact and future direction. So where did this lead to? In the same year this paper was published, free space quantum key distribution was already being extended to hundreds of meters by other groups. The physics scale. Then in 2017, 17 years after this experiment, China launched a MUCOS satellite and achieved a quantum key distribution from orbit to ground station, thousands of kilometers apart as to satellite. The author on this paper said this conclusion as that they saw no barrier to achieve exactly that. And that's right. They were right. On the other side of the thread, NIST, the US National Institute of Standards and Technology, published post-quantum cryptography standards in 2024 because quantum computers running Shor's algorithm can break RSA encryption. The exact threat this paper was building a defense against in 2000 is now global policy issue being addressed at the highest level of government and industry. The quantum internet research using entanglement to create fundamentally secure communication network is now an active field with $1 billion investment globally. This paper is a part of foundation that made all this possible. So classical cryptography security comes from computational hardness. Problems assumed to be difficult to solve but never proven. A fast enough computer or a quantum computer running Shor's algorithm breaks it. Quantum cryptography, this security comes from the laws of physics, especially that measuring a quantum system describes it. No amount of computational power changes this. Eves cannot intercept a photon without collapsing the entanglement, and cannot live without leaving a trace. So this experiment demonstrated that quantum cryptography based on entangled photon pair is not just theoretically sound, it's physically reliable. The protocol secured by Wells inequality testing detected every improper strategy attempted. The security guarantee is not mathematical, it's written in the laws of quantum mechanics itself. Thank you. This is it.